Hello, everybody. Welcome. So today we have a wonderful guest here, Mr. Matt Young from Raytheon, to talk to us a little bit about his area of expertise.
All right. Hello, everyone. My name is Matt. I am an engineering fellow with Raytheon, and my area of research at Raytheon is in computer vision. At Raytheon, we mostly use computer vision to help find objects of interest within military sensors. So this is typically enemy combatants, enemy combatant vehicles, those sorts of things. Those get used for both autonomous systems that we build, as well as for intelligence, surveillance, reconnaissance applications with the military. This presentation is a little bit of insight into some of the research that we're doing. I think it's really cool, interesting work. But it's got a very boring title, so just ignore the title. This is a presentation you can see from the date that I gave last year at the NVIDIA GTC conference, jointly with an NVIDIA employee that I work closely with on some work that we've been doing for generating simulated data to train machine learning models. So let's kind of start with the motivation here. So in the world of computer vision, models are very data hungry. So I think if you guys have any familiarity with machine learning at all, you probably already know that machine learning models are very data hungry, require a lot of data to train well, to get to good, robust solutions. Computer vision is a space in particular where this is a problem. Google published a paper in which they showed that the performance of a given computer vision model scales linearly with the log of the number of samples, meaning that you need an order of magnitude more samples every time you want to increase your performance just a little bit. So an enormous amount of data is required to continue to push performance out to better and better capabilities. And this study was actually done with just a fixed neural network size. So as we all know, neural networks have been growing and growing, getting larger, more computationally intensive, more parameters that have to be learned, and so that drive for more data keeps going up. Notice that this training data set size graph here is also on an exponential size, which shows that the amount of data that researchers and practitioners of machine learning are using to train their models just continues to grow exponentially over time, which leads me to the conclusion that no matter how much measured data you have, it will never be enough. So the hope is that someday there will be research breakthroughs that will reverse this trend. People will figure out ways to make more data-efficient machine learning models, and in fact that is an area of research, but no one has cracked that nut yet. All of the amazing capabilities that we're seeing out of the big tech companies like OpenAI and Google and other people like that are all being driven by a backbone of incredibly large data sets. In fact, if you go back and look at the research, almost every time there's a major research breakthrough where there's a step up in performance, it's because somebody figured out a way to process a much larger data set. So data set size is very important. So if data is the most important thing for machine learning, where does the data come from? So the most common place that data comes from for machine learning application is what's known as data sets of opportunity. This is what OpenAI uses, this is what Google uses. They're using data that somebody collected for a different purpose than machine learning. So obviously, in their case, they're scraping the internet, getting data off the internet, downloading books, whatever they can do to get more data. That data was not originally created for the purposes of training a machine learning model. It was made for other reasons. It was made because somebody wanted to post something about their cat on Reddit, right? And then the Google and OpenAI just harvested that data. Those are good places to get data because there is a lot of data out there. But the problem is that data will always be biased. It will always be a function of what people happen to be up to at the time that they generated that data. It's not necessarily the most well fit to the problem that you're trying to solve. And yeah, it's usually not an exact match to what the data will look like for your application. So when you're building a machine learning model for a particular application, you want it to do something, you want it to be used for a purpose. That purpose may be different than the purpose that the data was generated for that you're training it on if you use a data set of opportunity. So that's a problem. So what's the alternative? Well, you could go out and explicitly collect data. This is something that gets done a lot in industry. When you have a particular problem you're trying to solve and you want to build a machine learning model to solve that problem, let's figure out how we can collect data that's representative of that problem that we can then use to solve that problem. This is the approach that's currently being taken by a lot of the self-driving car companies. They have tons of vehicles out on the road, driving all the time, collecting data of what it's like to drive on the road. They spend an enormous amount of money on this. This is the problem with doing dedicated campaigns of data collection. It's extremely expensive. You have to set up instrumentation, you have to set up data collection devices, you have to store all that data, you then have to label that data because you need somebody to tell you what does this data correspond to, what was going on at the time that this data was collected. In the self-driving car case, was it a sunny day? Was it cloudy? What are they doing? Is there traffic? Is there a pedestrian? Someone has to go in and label all that, hand label all that, generate all the truth for you to use for your data. So dedicated campaigns of data collection are better than data sets of opportunity, but they are expensive, time-consuming, and slow. So is there another option? Well, the best option would be if we could just make our own data. Why don't we just make data? Then we will have exactly the data we need, when I need it, and at a reasonable cost. It's the holy grail. But the question is, how do you do that? So this is where synthetic data comes in. So there's a lot of interest in the past couple of years, a growing interest in synthetic data because people are running out of data sets. There was some articles published in the last 6 months talking about how OpenAI and Google have used up the internet. There's no more data to be mined there. They've used it all. And they're struggling to figure out where do we get data from next. And so one of the things that people are looking at, and us in particular, and I'll get to that in a minute, is the use of synthetic data. And here I want to spend a little bit of time just talking about semantics. So synthetic data would be any data that's not real. It's synthetic. But synthetic data can be broken down into a couple of different categories. So some people, when they use the term synthetic data, they are actually referring to data that gets generated by a generative AI model. So they will say, okay, we're going to synthesize text using ChatGPT, or we're going to synthesize images using Stable Diffusion, or we're going to use some other machine learning model, some generative AI model that's out there to create new data. So that's one approach. Other ways that you can create synthetic data is you can always blend or composite together existing data. So you can mix and match existing data that exists in the computer vision world. You know, that looks kind of like green screening together a scene, right? And this is a totally legitimate approach that you can use. You can do things like, again, getting back to the computer vision application, you can take an existing image, you can adjust the lighting, you can blur it out, you can do all kinds of things to create composite or blended data to increase the size of your data set. And then the third approach, which is the approach that I'm going to focus on in this presentation, is simulation. So simulation is a form of synthetic data. Sometimes people will use the two terms interchangeably, but really they're not interchangeable. Simulation is synthetic data that's produced by a simulation. And a simulation is some model, some usually physics-based model, a computer program that takes input and produces what it believes is a construction of a real-world simulation. So a great example of a simulation is like a video game, right? A video game is going to simulate a world that you can then interact with. A lot of the computer graphics that get used in movies, those would also be considered simulations. There's a lot of physics backing those computer graphics simulations. And this is an example of some simulated data that NVIDIA made using their autonomous driving simulation. They call it the Drive Sim. That looks very realistic because a company like NVIDIA that specializes in graphics processing has spent a lot of time building the physics models that are necessary to produce accurate and realistic simulation. So why can't we just use generative AI to create our synthetic data? Well, the problem with using generative AI to create synthetic data is that generative AI is itself a machine-learned model which was trained on some data. And as a result, to use a mathematical term, it's bounded by the domain of the data it was trained on. So any data that wasn't in the training data set, it doesn't know anything about. And if you want to generate some new sample that's completely different than anything it's seen before, it's not going to be able to accurately do that. So it's a problem when I'm trying to deal with a limited set of data. If I want to increase my total size of my data, all that generative AI is going to allow me to do is more finely sample my existing space. I can't go outside the bounds of the space that I was in, except with like a little bit of randomness, but randomness is not necessarily beneficial. So this is kind of been shown with these generative AI models by just how quickly they'll reproduce their training data if you try to tell them to reproduce their training data. So this is it being trained on a screen cap from the Dune movie and then producing that exact same image when asked for. So if I generate a bunch of images and I think I've gotten new data, I've probably just gotten some representative equivalent of the data that I already had. Another problem with generative AI models is they're, at the moment at least, they're kind of imprecise. They're getting better at this actually. It's in the years since I've done this presentation. So they'll produce samples that are similar to what you want but not exactly what you want, which is a problem for when you're trying to generate truth data to go along with your data for training. It's just not designed for this purpose. People are trying to use it for this purpose. I don't believe it's the best choice. So the advantages of using simulated data are that simulated data will give you precision. You will always be able to generate exactly the data you want. You can tell the simulation exactly what you want it to do, and it will do it. And so you can always know that your training data is exactly matched to the problem that you're trying to solve. Another advantage of simulated data is you get true ground truth. So all of your truth labels in your simulated data will, again, be exact. You don't have to worry about human labelers who may be sloppy with their bounding boxes or accidentally call a cat a dog or something like that that causes polluting in your training data. The truth will always be the truth. If you carefully construct your simulations, you can make it unbiased so that you can sample the space exactly how you want. You don't have to worry about, oh, I never drove my data collection car in the snow. You can just simulate snowy conditions. You can simulate a blizzard. You can simulate anything you want to ensure that you have full coverage of all possible situations, all possible data that you need to include in your model to ensure that your model is robust to everything that it might encounter. And that kind of gets into the diversity as well. It's not hard to sample data. You might drive a car around to collect data for 1,000,000 miles trying to get that one unique construction zone that was hard to navigate so that you could get that data in your training data set, but I could just create that construction zone in my simulated data. So you can make it as diverse as you want. And you can always increase that diversity pretty much at will. So some really great advantages of simulated data. And some people have started using simulated data, as I mentioned, to solve problems where they're dealing with limited data problems, where it's difficult for them to either harvest or collect enough data to solve their problem. So NVIDIA, of course, this is a presentation for NVIDIA GTC, so we're going to reference NVIDIA a lot. NVIDIA has built some nice tools. They have this Isaac Sim for autonomous robot training. It's a very realistic kind of warehouse environment with all the real physics of how boxes move and how you would pick something up or put it down and help people train warehouse robots. Also, it's rendered with physically realistic lighting so that those robots, they're going to have cameras on them to try to see the boxes so they can learn how to properly identify things with their cameras. This is one of several simulations that NVIDIA makes for generating data to train machine learning models. I already mentioned the drive sim is another one. Some other things people have done, this was a paper where they were simulating eyes to train a neural network for gaze tracking. And here's a paper where they literally improved performance of a self-driving car segmenter by training it on data from Grand Theft Auto 5. So I mean, even like, a video games are very realistic these days. You can use them to generate data that you can train models on that actually will transfer over to the real world. So here's an example. I'll probably have to go to the computer here. See if this will play. Oh, the video doesn't want to play. Oh, what a bummer. It's probably because I'm not connected to the internet. So this is, you can find this video on YouTube just showing NVIDIA's drive sim, and it's virtually indistinguishable from the real world, and then they show how they could take a real world scene and they could make it snowy, or they could do any number of other things to add diversity to the data set. So we've gotten very good at, again, we're talking about the computer vision application here, gotten very good at simulating the human visual spectrum, because that is a domain that a lot of people care about. That's what all of the video game developers care about. That's what all of the Hollywood movie developers care about. There's been billions, if not trillions of dollars invested in simulating the visual spectrum, and you can get very, very accurate results. The problem is that I, at Raytheon, work with sensors that are mostly not in visual spectrum. So a lot of military sensors are in either infrared or radio frequency or terahertz or other parts of the electromagnetic spectrum. And that creates a problem for us, because not only are we missing data, I can't go to the internet and download 100 billion images of infrared, but also I don't have the super duper high quality, high performance simulation tools either. And so this is where a company like Raytheon, working with a company like NVIDIA, we can collaborate to build a new set of tools to help solve these problems. And this is kind of some of the interesting work that we work on, is how do we build up these tool sets to solve these kinds of problems. So how do we do it? So in visual spectrum, the way it gets done is you have basically three components that you care about. You need complex geometry, so you need models of things that are sufficiently realistic enough, high enough polygon count, that they look real. It doesn't look like a very low fidelity box. It doesn't all look like Minecraft out there. You also need to have realistic materials, which means you need materials that interact with the light. They reflect it properly, they scatter it appropriately, you create the appropriate kind of shadows and things. So the material properties all need to be realistic so they can render correctly. And then you need to have dynamic lighting, which basically ray traces all the lights through the scene and sees how they bounce around, where are the shadows, where is it scattering, where is it reflecting, all those different information. So the good news is that moving from visual spectrum to a different domain, some of this stuff stays the same. I don't need to get new geometry. The geometry is just what it is. And so I can reuse all of that. The materials I can adapt, and the lighting I can also adapt. So fortunately, we can kind of stand on the shoulders of giants here and reuse a lot of existing capability to build new simulations for new use cases. So just to expound on that a little bit more, so again, the human visual spectrum, as we all know, is made up of wavelengths of light from about 400 nanometers to about 700 nanometers. And we tend to approximately break that down into the concept of, red, green, and blue when we're doing simulation. So usually when you're simulating something, you're simulating it in RGB space. And RGB space maps pretty well to the human perception of how we see colors. Now, if I'm going to one of my autonomous systems that might be using an infrared camera, well then I need to move from that 450 to 700 nanometers to whatever spectrum of light my camera is going to be actually detecting in. So the rest of this presentation is going to focus on work that we've done specifically for infrared. So infrared, to simulate infrared, I need to take all of the physics that's been developed for simulating visible light and I need to shift it to other wavelengths. So there's 3 bands of infrared that people typically use. There's what's known as shortwave infrared, midwave infrared, and longwave infrared. And they have wavelengths on the order of a few micrometers. And so the first thing we're going to need to do is we're first of all going to need to simulate light in that frequency band. And then we're going to have to simulate how that light interacts with objects in that frequency band. Well, unfortunately, in infrared, that light gets generated by a whole lot of different sources. In visible spectrum, our only light source is pretty much the sun during the day, and then at night we have various different artificial light sources. But most of those are kind of trying to mimic the sun anyway, so you get similar properties. In infrared, sure we have the sun, solar radiation right here. It produces a lot of infrared. It produces the most visible spectrum, but it produces a lot of infrared radiation. At the temperature of most things on the Earth, which is what they call ambient temperature, there's quite a bit of infrared radiation that gets produced, especially at midwave and longwave. So every one of us, every table, every piece of carpet, is illuminating this scene right now with infrared radiation because we're all giving off heat. Oh, and by the way, in addition to that, this is just the black body radiation. There's a lot of things also that generate heat. So you have a lot of heat engines, right? So human body is a heat engine. We're constantly burning up fuel and producing heat out of it. Obviously, in the military domain, we have, car engines and airplane engines and boat engines. Those produce a lot of heat. So that's another source of radiation, is literally heat generation. And so you have your solar radiance, you have back radiance off the atmosphere, you have emitted radiance from everything that's emitting, and then you have engine heat, and all that heat gets transferred around. If you touch something that's hot, some of that heat gets transferred to you. So you have heat conductance as well. So you have this hugely complex equation of different parameters that you need to simulate infrared to get your total heat balance. And then you need to account for that across a much wider wavelength than visible light. So it's a lot harder to simulate than visible light. But this is, in fact, kind of the process you have to go to if you want to use simulated data, because simulated data will only work if it's very close to measured data, if it's very similar to the data that you're actually going to be testing against. So here's just kind of some examples of how infrared can vary. This is so on the left-hand side is a SUV driving in a circle, on the right-hand side is a pickup truck driving in a circle. It's the same vehicle at the exact same location, and the only thing that's changing is the time of day and the orientation of the vehicle relative to the sun. So you can see in just one cycle of the day, sometimes the vehicle will look very dark, sometimes it'll look very hot. Here it's probably just reflecting a lot of solar radiation at us. Sometimes the background will be hot, sometimes the background will be cold, and you get a lot of variation. If I were looking at this invisible spectrum, it would probably look pretty much the same for all these images during the day, and it would probably look pretty much the same for all these images during the night. So I could probably represent it with just 2 variants. But in infrared, I have to consider all of the different variation that I'm going to get. And you can see that with, every target that you need to simulate. So we're going to have to generate like a huge amount of data to cover all of these spaces. So simulating that IR data with a high enough accuracy to be useful for training a machine learning model is going to require two components. One side is the high fidelity scene modeling, and one side is high fidelity sensor modeling. And the sensor modeling is a part that a lot of people don't think about when they're simulating data. So I do need to accurately capture all those heat equations. I need to know how hot everything is in the scene. I need to know what's reflecting infrared. I need to know what's emitting infrared. I need to be able to calculate all of that. I need to, that is associated with the materials. I need to understand how the weather is affecting things, how the location of the sun is affecting things, etc. Get the world model figured out. But that's only, as it turns out, half the story, because I'm now going to image that with a camera. And it turns out that this is true in visual spectrum as well. We just kind of tend to ignore it. So when you're simulating data, you want to simulate not only the state of the world, but you want to simulate the state of the sensor that's capturing the world. So if you have a camera, even with a visual spectrum camera, that's going to have different sensitivities. It's going to have different lensing that's going to cause blurring effects. It's going to cause vignetting and various other effects on your image. You want to make sure that you capture all of that in your simulated data. And the good news is, again, the tools can do that for you, but you do want to make sure that you model that, because if you don't, then you end up with simulated data that it looks a little too real. You end up in kind of that uncanny valley where it's like, I can tell that's not quite real. And usually if you can tell it's not real, the machine learning model can also tell it's not real. And it'll learn stuff that won't work in the real world. So you do have to be very careful with the simulated data generation. So for the other side, you do need to model your sensor as well. You need to know how are your pixel detectors, how sensitive are they, how do they convert that light energy into pixel values, what does the lensing look like, what kind of noise do I have, how does it work in terms of, does it take a single snapshot or is it kind of a continuous stream of data? These are all important things to model. So you can see we end up with a very complicated model that we have to make to do a high fidelity simulation to generate this data. So this is why, we work on these things, because this stuff doesn't just work out of the box. So I find a lot of this pretty interesting. So as I mentioned, when we're creating a realistic IR scene, we can reuse the geometry. We kind of have to redo the materials. We can reuse some of the lighting components. I'm going to skip this one. So the good news is we have this traditional rendering pipeline that's available to us from Visual Spectrum that does all of these nice things. It does, your visibility, occlusion mapping, scene geometry, projection, color shading, material mapping. This is all stuff that NVIDIA has out of the box, ready to go. You could do this in Blender, right? Real easy stuff to do. It's all done for you. People have built these models. And so I got all this stuff available to me. This is great. And the nice thing is to convert that to IR, I really only have to take what exists and add a few boxes. I have to do some work over on this side to model some of the heat transfers, some of the heat generation elements. I have to do a little bit of work here to account for the fact that IR is a wider band of energy than visual spectrum. So I have to capture a wider set of frequency bands propagating through the atmosphere. And then I basically have to replace my camera model with a new camera model that's representative of IR cameras. And so, as it turned out, NVIDIA basically did all this stuff for us. I hired a small business to do this, and then Raytheon did all this stuff based off of our knowledge of working with infrared cameras. And so we're able to put something together relatively quickly by taking advantage of things that already existed and just adding the unique capabilities that we needed for our particular use case. And I guess the point of this slide, and I won't spend too much time on this slide, is that one thing you have to keep in mind when you're doing this is we focus on the highest fidelity of modeling that we can get. So we're treating this more like what you would consider to be a movie renderer. This is a non-real-time renderer. We're asking it to chunk away until it comes up with the highest accuracy result. We're not trying to render stuff in real time. So when you're doing simulations, if you're doing a video game style real-time simulation, it will always make trade-offs in terms of accuracy to achieve frame rate. And so we did set this up specifically as a sort of traditional, very slow renderer. And this is just getting into more details on how we model the materials. So NVIDIA has this approach. These are a lot of NVIDIA slides. NVIDIA has this approach that they call physics-based rendering, or PBR, and they were trying to draw the distinction between physics-based rendering and what they call physics-accurate rendering, where you're trying to ensure that we get that band-accurate response. You're trying to not get something that just sort of looks okay, but something that's actually an accurate simulation, an accurate prediction of the result that you're going to get. And so this is a little bit of detail, again, on the NVIDIA side of how they did that. And if you want to understand exactly, because I don't understand exactly, you can watch the NVIDIA presentation. And then, of course, we needed to spend some time building some realistic scenes. So the good news is there's a lot of tools out there now to help you build complex, realistic, accurate scenes. There's randomized terrain generators that you can get that will give you really realistic looking terrains. There's also terrain servers where you can go and download actual real world terrain. So Raytheon, we're located in Tucson, so we did some simulations of the Tucson mountains and our plant site nearby to show that we could accurately simulate the real world. You can use a physics engine to generate wave clutter. So this is, I think this is video. Let me see if it'll play. Yeah. So this is an example of one we did where one side is measured data and one side is simulated data that we were trying to make look like the measured data. So we were able to create the wave clutter, and one of the interesting things about wave clutter is in infrared, when you get that white foam. So if you stir up the water enough to get some foam, it's much, much brighter in infrared than just regular waves. So it's accurately simulating that foam and representing that it's brighter. So this is the measured data and this is the simulated data. So you can see, we're able to simulate all of those effects accurately enough to produce simulated data that if I showed you this without that, you would be pretty convinced that this is real and that one's fake. And by the way, this one is actually the simulated one. So again, we can get it accurate enough that, in the absence of the other, it would be very hard to tell that the one is simulated. We're getting the reflection of the ship off of the water surface in front of the ship and all these different things. Most of this was, again, tools that NVIDIA had already built for various other reasons, and we just had to adapt them to work properly in the infrared domain by updating some of the parameters and updating some of the methods of simulation. And then this one, just we had to update the atmospheric models to account for how well infrared transmits through the atmosphere. So similar to how a cloud will block visible light somewhat, it'll also block infrared. Rain will block infrared, but it'll do it a little bit differently than visible spectrum, so we have to update all those models to properly make sure that the infrared is transmitting through the atmosphere correctly. Here's the NVIDIA pitch. So hey, guess what? Turns out all this simulation requires a lot of compute power. So we did all of our simulation using NVIDIA GPUs. We have a fairly sizable GPU farm down in Tucson that we bought and stood up solely for the purposes of training machine learning models. It was several years ago, so now it's looking kind of pathetic compared to what OpenAI and XAI are doing. But we have about 200 NVIDIA A100 GPUs that we have dedicated to this stuff. It was a lot at the time, I promise. And so, but you know, you need that. So the NVIDIA GPUs, the reason NVIDIA has grown so much, and the reason that NVIDIA is now one of the most valuable companies in the world is because their GPU products legitimately do run all this stuff much faster. And when you're in a situation like I am, where you need the GPU both to simulate your training data and to train your machine learning model, we're double dipping, and it's like twice as much compute that we need. So if anybody knows an alternative to NVIDIA GPUs, I'm happy to listen, but that's kind of what we're using these days. And NVIDIA, of course, they're a great company. They have wonderful customer support, and they've helped us out a lot. But yeah, this is just them showing how much they were able to accelerate our simulation using the GPUs. And some more eye candy on some different infrared simulations we've done. So this is a fighter jet, there's a cruise missile, and some other things. And for what it's worth, this presentation is focused on infrared, but we've done all of this same work over again for radar. And our two products that we've developed is GenIR and GenRF that can simulate infrared and radar. And then GenWorld is the sort of world model that those sensors populate. Oh, I have a clip. Okay, so how does it work? So I would love to stand here and tell you, hey, guess what? We made this simulated data thing, and the performance is perfect. It's amazing, right? In reality, you know, there are still fidelity losses between simulated data and measured data. There's still model geometry differences. Nothing is perfect. But what we have shown is that we can perform better by using simulated data combined with measured data than we were able to get with measured data only. And so it is helping us with our performance. So with measured data, we were able to get, this is for, what was this for? This is for detection of military vehicles and classification into different vehicle types. And with measured data, we went out and we collected a bunch of data. We flew in a helicopter and collected a bunch of data. And when we tested against similar conditions, we were able to get pretty good performance. But when the conditions changed, when we went and flew the helicopter at a different test range, you know, the performance kind of tanked. And the performance also tanked when we flew it at a different time of day. So that was bad. So we said, okay, we're going to replace it with simulated data. And what we determined was, well, the simulated data was actually able to perform about the same, which was kind of surprising. I was hoping it would help more over on these ends. But when we took the simulated data and we said, okay, let's fine-tune it with measured data so that it kind of learns basic features from simulated and then understands a little better about what measured data looks like. Well, then we were able to outperform the measured only even for the same background. And when we changed backgrounds or changed time of day, then we all of a sudden saw a lot more robustness in our performance. So this was kind of where we were last year. We're continuing to work on this. We're always iterating, improving the simulation, improving our machine learning models, and continuing to work on this. So that is all I have in terms of presentation. Yeah, so where do we go from here? Results are showing promise. There's still a long way to go. These results, I should say, were generated with about 3 million simulated samples. So still not as many as I would like. I recently did a new study where we generated 218 million samples, but I don't have those results publicly released to show, so I can't show them to you. But you know, that's one of the nice things about simulated data is once you kind of get it dialed in, you can just keep generating more samples. And so you can fill those holes in your training data and keep trying to make it better. One of the places where we lack, we need more capabilities on the scene construction side, because I need to be able to procedurally generate realistic scenes with complex characteristics. Right now I'm using canned scenes, and I think that's kind of limiting our performance. There are tools out there for that, we just haven't integrated them into our tool set. The latest thing we've been working on is how do we calibrate a simulation. So how do we take simulated data and figure out what its deficiencies are relative to measured data, and try to tune out those deficiencies. So that's a big area of research for us. Methods to create a comparison function that we can use to update sim parameters, or maybe do some post-processing on simulated images to try to make them more realistic and line them up more closely with measured data. So this is still a very active area of research for Raytheon, something that we're working on, doing new stuff in every day. So I'll take any questions.
When you're training models off of simulated data, how do you verify that millions of simulations are correct so that you're training models on correct data?
Yeah, that gets to the thing I was saying at the very end about calibrating the simulation. So that's a hard thing to do. We have two approaches we use. The first approach is the approach that everyone uses, which is we try it, if it doesn't work, we change something, and if it doesn't work, we change something else, and then we keep changing it until it works. But the more better thing that we do, the military actually does have an approach for what they call simulation validation that gets used outside of the context of machine learning. But we do a lot of simulation to predict the performance of military things against battlefields that don't exist today, right? And so the way that they do simulation validation is actually they will build a simulation, and then they will construct a very careful set of scenarios in that simulation that are going to be an exact match to in a set of scenarios you're going to conduct in the real world, usually on a military test range. And you will run your simulation, and you will predict what you're going to see. And then you'll go do your test, and then you'll analyze and compare what you actually saw versus what your simulation predicted you would see. And where there are discrepancies, you have to basically write up this plan of action for how you're going to update the simulation to account for the discrepancies. And that's actually, as it turns out, where a lot of our very detailed models have come from, have been that simulation validation process where we've gone out with an IR camera and we've collected data, and it was like, oh, whoa, there's this weird streak in the IR camera. And we discover it's because this IR camera was like right up next to a hot battery or something, and that was spewing out thermal radiation. So we're like, oh, now we have to add that to the simulation to make it accurate to predict that. And that becomes a new simulation model we can use in the future. And so it's kind of a long process of mostly direct comparison with measured data. Any other questions?
I just had a question on how you decided on, because you were saying that NVIDIA is the best. You prefer it for not only training but also like holding, I forget the correct terminology, but holding the models themselves. So was there like a series of trial and error with different types of like chips and processors, or did you just like NVIDIA's like, how did you guys land on NVIDIA being the best of the best?
So, we started with NVIDIA for our simulation work for machine learning was really a big thing. And we were part of some work that NVIDIA was doing about maybe a decade and a half ago, where they already existed as a video game graphics card company, but they wanted to expand their business beyond just video games. And they started developing a set of libraries for their cards. So NVIDIA's cards, you can think of them under the hood as being just linear algebra accelerators. And they started developing a set of programming libraries to allow you to use a GPU for purposes other than just real-time rendering of a video game. And they actually came up with a name for that no one uses anymore. They called it a general purpose GPU, or a GP GPU, and we used to call them GP GPUs for a while. And we used all of those libraries to build our simulation tools, working with NVIDIA, because NVIDIA's always had software services reps that will help you build applications if you buy stuff from them. And built up a lot of our simulation tools that way. On the machine learning side, it was similar. NVIDIA looked at this kind of rise of deep neural networks and they said, hey, there's another potential market for us. And they started building tools for supporting machine learning. And then just kind of the industry as a whole just kind of adopted them. And that's what all of the tool sets for accelerated machine learning training have been built for. All the tool sets for PyTorch, for TensorFlow, to maximize their speed in training have all been built for NVIDIA GPUs, mostly by NVIDIA employees, but also by a very dedicated open source community building these tools. And so they just kind of became the de facto standard. So that one was handed to us. And there are other companies out there trying to build alternatives, trying to get a piece of that market, trying to break NVIDIA's stranglehold. And we do look at those, and I, in fact, have a research project where we evaluate alternative chips. But kind of to date, nobody does as good of a job.
Yeah. Okay, thank you so much. That's interesting.